Hello. Hello. Welcome to the live session of this NPTEL course, Waste to Energy Conversion. This is live session number 8. My name is Devarun Banerjee. I'm a PhD PMRF scholar of Indian Institute of Technology, Delhi. Okay. So, in this week's lectures, basically the first lecture discussed a bit of some of the sample problems, a bit of them we'll discuss in this today's live session. Apart from that, some lectures covered the algal cultivation. So the contents are like why algal cultivation is important, algal metabolism and synthesis of fat and protein, classification of algae, lipid content in algal cell, algal lipids and biooil quality, conditions influencing algal lipid quality and quantity, enhanced lipid accumulation, cultivation and growth of microalgae as an important step for algae to oil, reactor systems for cultivation and growth of microalgae, harvesting of algal biomass, treatment of wastewater. So, what is algal? Why algal biomass? So, because these are important metabolites which have. So, from microalgae, there are different segments. There are different composition, vitamins, proteins, carotenoids, lipids, carbohydrates. Those are important things which we can get from microalgae. Okay. Apart from that, the pigments and cosmetics which we can also get, and they have the application in health, food, and feed additives. Cosmetics for energy production also. So some features of algal biomass are like their rapid growth in saline on brackish water. Some species produce high yields of lipids. They use all nutrients, minimize eutrophication. They require CO2 for growth. Therefore, the fuel is carbon neutral. Algal biomass can be used as fodder or and manure. Uh, these are basically very much diverse species, untapped resource basically with high potential. If you see the algal metabolism, microalgae grow like plants photosynthesis, during which it captures CO2 and photons. The photonic energy, water and CO2, these are converted into sugars. And then these sugars are basically converted into macromolecules, uh, such as lipids, carbohydrate, protein. So if you see the basic reaction of this particular algal metabolism, it is like 6 CO2, 6H2O, and for 1 mole of sugar production, there are 8 photons are required, and then these particular sugars are converted to macromolecules such as lipids. So the lipid containing algae, it contributes to the bio-oil. So basic metabolic pathways, if you see, of algae for biofuel production, so there are this kind of different pathways are there, like Kelvin, one of those are like Kelvin cycle, where CO2 is taken as the feed, and from that there is the starch synthesis takes place, and from that the starch is produced, and then alcohols and organic acids are produced. Uh, and further simplified scheme are being actually shown here for the lipid synthesis from the microalgae. And then there are like different microalgae that are present. So for example, there are green algae, red algae, blue green algae, these kind of different microalgae are present, in which there are different properties they have, and due to that their specifications and their uses also different. Like green algae, they have basically the green chloroplast, which contains chlorophyll and xanthophyll as their accessory pigments. These cells have mitochondria, and some species of them have flagella. On the other hand, the red algae have the chloroplast with chlorophyll and phycobilins. So these kind of, as I told, the specificities are different, and their properties are different. Apart from that, there are other algae also, like brown algae or Phaeophyta, diatomaceae, and these are also different types of other microalgae. You can check the further details. These are more into like the biological parts. Okay. Hmm. And some case studies of these kind of different algae are shown here. From which kind of algae there are, how much amount of biomass productivity can be there, and how much lipid productivity can be there. Like this kind of details are shown here. And then the typical lipid content in different types of algal cell are also shown here. And basically it's a more or less a untapped uh, resource for fuel generation. So more and more research is required to identify the microalgae having the high lipid content. For example, like this Schizochitrium, these have a very high lipid content, about 77% of lipid, 77 grams of lipid per 100 gram of dry algae is reported. Also the Botiococcus brownie, this have also a high amount of lipid, up to 75 grams, 75% of lipid. So more and more research are actually being carried out in this direction. And then the various types of fatty acids in algal cell are there. Like the saturated fatty acids. This can be divided into saturated fatty acids and unsaturated fatty acids. Among the saturated fatty acids, there are these type of fatty acids are there: capric, lauric, palmitic, stearic, myristic, lignoceric, behenic, arachidic. And the unsaturated fatty acids like palmitoleic, sapienic, myristoleic, oleic, linoleic, like that. These kind of unsaturated fatty acids are uh, also can be obtained from the microalgae. Apart from that, the octadecatetrinic, arachidonic, icosapentonic, erucic, these are also other unsaturated fatty acids. And then basically there is an important thing that there is a correlation between the fatty acids and the Cetan number. So the Cetan number of various fatty acids present in algal oil are shown here. Cetan number actually denotes the quality of the obtained bio oil or obtained fuel. So based on the depending on the fatty acid, it basically this bio oil quality or the Cetan number also varies. Okay. There is also effect of the nitrogen source and the composition of fatty acids are also very important parameter. There are different strategies for enhanced lipid accumulation in microalgae, like the physicochemical methods and molecular level strategies. Okay. And then the cultivation of microalgae as an important step for algae to oil is shown here. The biomass productivity, if you see as the output parameter, is represented as the biomass concentration difference with respect to T2 and T1 time, x2 minus x1 divided by T2 minus T1. And lipid content percentage of it is shown in the form of ratio of weight of extracted lipids and dry algae biomass. Lipid productivity is equals to the biomass productivity multiplied by lipid content in percentage. Okay, that was the first lecture of cultivation of algal biomass. Then, if you see the second lecture, there discussed about the different reactor systems. So let us check some questions and then we'll come to that lecture. First question is, which of the following is not an example of saturated fatty acids? Capric, stearic, myristic, oleic. The correct answer is oleic acid. So oleic acid is not an saturated fatty acids. On the other hand, capric, myristic, stearic. These acids are all saturated fatty acids. So oleic acid is an unsaturated fatty acid. And then let's see a problem, numerical problem. 50 gram of waste cooking oil was fully dissolved in some amount of neutralized ethanol by heating and titrated with N by 10 KOH solution using phenolphthalein indicator. If the titer value is 100 ml, determine the acid value of the oil. So there is the direct formula of acid value in the 56.1 into V into C by M. V is the volume of KOH employed for titration. C is the concentration of KOH used for titration. M is the weight of the sample taken to be analyzed. So you just have to put the values. Okay. So V is the volume of KOH. So here if you see volume of KOH is 100 ml given here. Concentration of KOH, which is the N by 10, which means the 0.1, and weight of the sample, that is the 50 grams M. So just put the values and you'll get the acid value of the bio oil. It's 11.22. And these kind of problems can be given to you, small problems. You just have to get the concept of the acid value formula. Check the original slide lectures. Another problem. A 200 ml bio-oil sample is reacted with 81 gram iodide monochloride. After reaction, potassium iodide is added in it and the liberated iodine is titrated with sodium thiosulfate. If 0.2 mole of sodium thiosulfate is consumed to reach the titrate value, determine the iodine value of the oil. So let us see the solution. So basically the excess iodine chloride will react with the potassium iodide and form iodine, which will further be converted to iodine. Okay, uh, atomic iodine. So this is ICl plus Ki gives us KCl plus I2 iodine, and I2 plus Na2S2O3 sodium thiosulfate gives sodium iodide NaI plus Na2S4O6. If you see the stoichiometry of the reaction, then the zero point 0.2 mole of thiosulfate reacts with 0.1 mole of iodine. See here is 2:1 ratio. 2:1 ratio. So given like 0.2 mole of sodium thiosulfate is consumed, right? So converting it from the molecular weight iodine, so 253.8 into zero point 0.1 gives us 25.38 grams of iodine. In the original iodine chloride solution, iodine present is again the similar way is 63.31 gram, and the iodine consumed by the through 200 ml of bio oil is so this minus this 53.31 minus 25.38 is 37.93 grams. So this coming the iodine value of the oil is 19. So there are different reactor systems for cultivation of microalgae. Hmm. There are the closed photobioreactor and open system photobioreactors. So closed photobioreactors examples are vertical tubular, horizontal tubular, plate type, plastic bag systems. These are the major types of closed photobioreactors. And there are the different further detailing of these closed photobioreactors are shown here. Okay, horizontal tubular photobioreactor, vertical column photobioreactor, flat panel photobioreactor. These are the different examples are shown here, and then basically the comparison between the open and closed photobioreactor are shown. So open photobioreactor has a disadvantage of high space requirement, and also there is a high amount of water loss is there in the open case. Whereas these are the advantages for the closed photobioreactor. So it requires a smaller space, water loss amount is low, CO2 loss is also low, but it requires some gas exchange devices because the oxygen must be removed, so that we need to prevent the inhibition of photosynthesis or oxidation reaction basically in this kind of case. And some additional cost is there for regarding the cooling. So cooling is often required in the closed photobioreactors. On the other hand, in the open case, the temperature is actually highly variable, and some control is possible by the pond depth. So these are the some comparison point of views, and also there is no issue of cleaning in the open photobioreactor, but in the closed system, some cleaning is required because the wall growth of different algae and different this kind of unnecessary things, uh, to remove them, and the dart which gradually gets deposited on the wall, they reduce the light intensity. The contamination risk in open pond and open photobioreactor is also very high. On the other hand, it is comparatively low. There's a low contamination risk in the closed system. Mm. Also, the biomass quality is highly variable for open system, and the biomass concentration is required is low for open system, but this is very much high for closed system. And also the flexibility in production is also high for the closed photobioreactors. Okay, and then there are the different types of closed photobioreactors. Comparison different from different point of view are shown here, like tubular type, column type, flat panel type, and these are shown in different parameter level: low, medium, and high. And the parameters are biomass yield, manufacturing cost, export surface area for light illumination, problem due to oxygen and CO2 accumulation, scale up possibility, maintenance cost. These are the different parameters. And some typical dimensions of various types of photobioreactors in the research scale are shown here, like open pond type, horizontal tubular photobioreactor, vertical column type, flat panel type. This. And then the harvesting of algal biomass is shown here, the process of harvesting. So there are different processes are there for harvesting and their subsequent thickening. So sedimentation, flocculation, flotation, these are some important processes. And from the after the harvesting, when water is removed, the biomass we are getting, algal biomass, it is much more concentrated. Then this concentrated biomass goes through a thickening process to remove further water and to further improve its concentration and quality. So these processes are the centrifugation, ultrasonication, ultrasonic agitation, filtration. This kind of thickening processes are also there. And based on that, these are the different unit operations which are shown here, like flocculation, and further detailed of the mechanism of flocculation you must check them. The flotation, sedimentation, these are the different processes, different unit operations are there in algal biomass harvesting. And then the thickening processes like the centrifugation, ultrasonic agitation, filtration, some basic processes are there. And some techniques as already uh, discussed, the filtration, like specifically vacuum filtration, tangential flow filtration, or like through basically a membrane process. This kind of filtration is carried out, and we get a very high amount of like recovery, 70 to 89%. However, depending on the microalgae species, these methods can also be varied, and depending on the requirement and how much amount of recovery is required, centrifugation can also be a very important and uh, efficient technique for a high recovery. So, in fact, you can get more than 90 to 95% recovery of your biomass from this. Okay, and apart from that, the dispersion, flotation, flocculation, these are the also different methods. It's just example, case studies are shown here. Gravity sedimentation, flocculation, like that. And then this basically the comparison between these different harvesting techniques are shown here. Then gravity sedimentation, inorganic chemical flocculation, centrifugation, filtration, flotation, based on the yield, relative cost, energy uses. These are actually shown. Okay. Which of the following is not a type of closed system photobioreactor? Vertical tubular, Horizontal tubular plastic bag systems, raceway pond. So the correct answer is raceway pond. Raceway pond is an example of open system photobioreactor. On the other hand, vertical tubular, horizontal tubular, plastic bag system, these are all examples of closed photobioreactor. Flat panel photobioreactors typically have a width of dash centimeter, 5.5, 3.2, 8.5, 10.5. Correct answer is 3.2 centimeter. Flat panel photobioreactors have a typical width of 3.2 centimeter. Among the following algae harvest method, which one has relatively low cost? Inorganic chemical flocculation, polyelectrolyte flocculation, gravity sedimentation, flotation. Correct answer is gravity sedimentation, which has the relatively low cost among these options. Inorganic chemical flocculation, polyelectrolyte flocculation, flotation, these are all having high relative costs. So the final portion of this particular course is having this content. Biodiesel as an important option for energy production from algal biomass, bio-oil production from algal biomass, conversion of algal oil to biodiesel, types of conversion process mechanisms and comparisons, factors affecting biodiesel yield, upgradation of algal oil to biodiesel using homogeneous and heterogeneous catalysts, quality parameters of algal biodiesel and its stability, challenges for microalgae and integrated system scheme for utilization, biojet fuels, research status on algae 2 oil. So we'll check the lectures first. So important energy production routes for algal biomass, and these can be converted into biodiesel, biojet fuel, syngas, biogas, pyrolysis oil, etc. Algal biomass can be converted into bio oil via oil extraction. Then bio oil can be upgraded, and upgradation and blending can take place to biodiesel and or biojet fuel. The conventional route for bio oil production from bioalgal biomass is like this: via drying, oil extraction and separation techniques. And this is the basic schematic diagram of the mechanism of oil extraction using solvent. Then the further details, operating conditions and solvent which are used in the extraction of microalgal lipids using organic solvents process. And then another process for extraction is the supercritical CO2 extraction. Here a basic schematic diagram of the supercritical CO2 extraction mechanism is shown, and again it's bit of case studies, operating conditions, and some important inferences which we get from it are like this: the increase in lipid extraction with pressure at constant temperature, and increase in lipid extraction rate with temperature at constant pressure. And here some people have done the optimization study, and they have got an optimum condition of about 400 bar, 13.7 ml ethanol, and 60-minute conditions. Similarly, lipid yield increased with pressure at constant temperature. So yield it's proportional with the pressure, whereas it is inversely proportional with the temperature at constant lower pressure. However, at high pressure, it increases with temperature. It's a very interesting inference or observation which the researcher has got. A similar effect of temperature and pressure on the total lipid yield have also been observed. Then there is one mechanism of single step oil extraction technique. The screen got freezed. Actually, I didn't realize. Okay, so we are here. The single step oil extraction. Apart from that, the biodiesel production route via the trans-esterification and then subsequent filtration or distillation technique is also there. Basic mechanism of trans-esterification is shown here, where triglycerides react with alcohol on a suitable catalyst to produce the esters and glycerol as byproduct. Different types of trans-esterification processes. So there are catalyzed trans-esterification process. Among it, there is homogeneous base catalyst, homogeneous acid catalyzed, heterogeneous base catalyzed, heterogeneous acid catalyzed, mm, and enzyme catalyzed. So these are the basic types of catalyzed uh, transesterification process. Okay, and different other processes like oscillatory flow reactor assisted transesterification, microwave technology assisted transesterification, ultrasonic technology, co-solvent method. So there are different mm, new age methods for the biodiesel production. And then there's the mechanisms of these type of different techniques like base catalyzed, acid catalyzed. Okay, these are shown here. And there are the different factors which affect the biodiesel yield, like are the oil temperature, reaction temperature, ratio of alcohol to oil, catalyst type and concentration, intensity of mixing, purity of reaction. That's the different factors. And here the comparisons between the base, acid, and enzyme catalyzed esterification reactions are shown. Among them, the advantages and disadvantages are also shown of the different types of transesterification process. Some basic case studies are also shown here for the upgradation of algal oil to biodiesel. What type of extraction method are used, what type of catalyst is used, and how much biodiesel conversion and lipid content percentage are actually obtained. Okay, and similarly, as the extraction method, then like homogeneous catalyzed method. Similarly, the heterogeneous catalyzed method, like calcium oxide supported on alumina, magnesium oxide supported on alumina, magnesium zirconium solid waste catalyst. These are the different catalysts which are used for the biodiesel production using heterogeneous catalyst. And then the basically the difference of homogeneous and heterogeneous catalyzed transistor processes based on the factors like reaction rate, post-treatment step, cost, catalyst reuse, presence of water or free fatty acids, processing methodologies like that. Okay, and then further examples of jet fuel, biojet fuels, production of biojet fuels via different routes. These are shown. So last few questions we'll discuss. Which of the following catalyzed transesterification process are used for biodiesel production? Homogeneous base catalyzed, homogeneous acid catalyzed, enzyme catalyzed, all of the above. So as discussed, the correct answer is all of the above. Homogeneous base catalyzed, homogeneous acid catalyzed, enzyme catalyzed, all of the above are the processes used for biodiesel production. Select the factors which affect the yield of biodiesel: oil temperature, reaction temperature, catalyst type and concentration, all of the above. Correct answer would be all of the above. It is also discussed. These are all the factors which affect the biodiesel yield. You can pause the video, recorded video, and check the question. Which of the following statement is not true about microwave technology assisted catalyzed Esterification. Energy requirement is less. Scale up is easy. KOH is used as catalyst. None of the above. So correct answer is scale up is so easy and not true about microwave technologies. So scale up is difficult actually, but energy requirement is actually less and KOH is used as catalyst. But scale up is actually a difficult thing for microwave technologies. That is why still, despite of having a low reaction time, low energy requirement, industries still use the conventional, uh, the high pressure fixed bed reactor or batch reactors, like not the microwave ones. So last question: which of the following is not a type of homogeneous catalyst used for the upgradation of algal oil to biodiesel? HCl, H2SO4, NaOH, and calcium oxide supported on alumina. The correct answer is calcium oxide supported on alumina, because this is the heterogeneous catalyst. The rest of the all are the homogeneous catalysts. HCl, H2SO4, or NaOH. These are all soluble in the sample. But this alumina supporting on the for the calcium oxide is a heterogeneous catalyst for biodiesel production. Okay, so that's all from my side. Since no one is here in the meeting, um, okay, I'm stopping today's meeting then. Thank you.